Students, welcome to Sunil's tutorial. I'm Sunil Milwangi and today we'll be doing this chapter called as current electricity. Let's see a Wheatstone network. Now, what is a Wheatstone network? A Wheatstone network is a simple network device to know the value of an unknown resistance. It is a simple circuit. It is a simple circuit to determine the value of an unknown resistance. Right? Now, what does it consist of? Let's see a Wheatstone network. Let's first see the circuit diagram for this. It consists of 4 resistors. It consists of 4 resistors which are connected across an EMF key, and you have a galvanometer. Let's consider that these are points A, B, C, D. Let's consider resistance R1, R2, R3 and R4. Right? So this is your galvanometer. You have current entering from this junction, current moving out. Let's assume that this current here is I1, this current is I2, right? So current I2 comes back here, current I1, and they meet and you get your current I again, right? So it consists of 4 resistors R1, R2, R3, R4. It consists of 4 resistors R1, R2, R3 and R4, right? They are connected to form a closed circuit ABCD as shown in the figure. They are connected to form a closed circuit ABCD as shown in the figure. Right? Now, cell E is connected between 2 diagonally opposite junctions A and C. Cell E, this is your cell E, is connected between two diagonally opposite junctions A and C. Fine. Now, there is a certain point along the branch ADC which is at the same potential as that of the potential of point B. There is a certain point along the branch ADC. There is a certain point along the branch ADC which is at the same potential, as that of the potential, which is at the same potential as that of as that of the potential of point B, right? So if I connect a galvanometer across these 2 points, the galvanometer should show zero deflection, because if I assume, let that point be D, let that point be D. That means if point D and point B are at the same potential, and if I connect a galvanometer across them, the galvanometer should show zero deflection. So I can say that, thus, if a galvanometer is connected, if a galvanometer is connected, between points B and D, it will not show any deflection even though current flows through the rest of the circuit. It will not show any deflection even though current flows through the rest of the circuit. Current flows through the rest of the circuit. Even though current flows through the rest of the circuit, right? In such a case, I can say that network ABCD is balanced. In such a case, network ABCD is balanced, right? And the galvanometer is set to show null point, and the galvanometer is said to show null point. Fine. Now, let's assume that, let's get the condition for a balanced galvanometer. Let us assume that I is the current supplied by the battery. Let I be the current supplied by the battery. Let's assume I is the current supplied by the battery. Now, as it approaches point A, it gets divided into 2 parts, I1 and I2. As it approaches point A, it gets divided into 2 parts, I1 and I2. It gets divided into 2 parts, I1 and I2. Now, current I1 flows through R1 and current I2 flows through I3, right? I1 flows through R1 and I2 flows through R3, right? Now, in this case, I can therefore say that when the network is balanced, there is no current flowing through B and D. When the network is balanced, there is no current. There is no current flowing between B and D. There is no current flowing between B and D, right? That means these 2 points will be at the same potential. Hence, the entire current I1 will flow through R2, since points B and D are at equipotential. The entire current I1 will flow through R2 and I2 will flow through R4. Fine. Now let's assume that let VA, VB, VC and VD be the potentials at point AB, be the potential at points A, B, C and D. Be the potentials at points A, B, C and D. Right? Now, we've already said that potential at B is equal to potential at D. That's your balance condition, right? That means I can therefore say VB is equal to VD, right? Now, multiply by -1. If I multiply by -1, I get minus VB is minus VD. If I multiply by -1, this is what I get. Now, add VA to this, so I'll get VA minus VB is VA minus VD, right? Now, similarly, I can also say that, let's call this as equation 1. Next, I can say again, we know that VB is equal to VD, right? Subtract VC from it. So I'll get VB minus VC is VD minus VC, call this as equation 2, right? Now, once I have this, then if I apply Ohm's law, I can say by Ohm's law, VA minus VB will be nothing but I1 R1. The potential drop between these 2 points will be I1 R1. Next, VA minus VD is going to be nothing but I2 R3, right? Similarly, VB minus VC is going to be nothing but I1 R2, and VD minus VC is going to be I2 R4, right? Now substitute the above values in equation 1 and 2. So in which case I'll get I1 R1 is equal to I2 R3 and I1 R2 is equal to I2 R4, right? Call this as equation 3, call this as equation 4. Divide 3 and 4. So I'll get I1 R1 upon I1 R2 is I2 R3 upon I2 R4, right? Therefore, you will get R1 upon R2 is R3 upon R4. That's your balancing condition. This particular relation is called as the balancing condition. This relation is called balancing condition. Fine. So, if I know the value of 3 resistors, using the balancing condition, I can find out the value of the 4th resistor. Right? Do we get this thing clear? Next, let's see a couple of numericals on Wheatstone network. Take down the numerical. Four resistors of 4 ohms, 4 ohms, 4 ohms and 12 ohms. Four resistors of 4 ohms, 4 ohms, 4 ohms and 12 ohms are connected in a Wheatstone network. Find the resistance which when connected across the 12 ohm resistor balances the network. Which when connected across the 12 ohm resistance balances the network. Now guys, if the network is balanced,
so there is no current flowing through.
you need not show the current block. I only want to find out what is my balancing resistance. If the network is balanced, then I can say that R1 upon R2 will be R3 upon R4, that is 4 upon 4 will be 4 upon R4, right? In which case I'll get R4 is 4 ohms, but R4 is nothing but the 12 ohm and X in parallel, but R4 is 12 ohm and X in parallel. If they are in parallel, their equivalent resistance will be 1 upon R4 will be 1 upon 12 plus 1 upon X. Now you can solve this and get the value of X. Fine, do we get this in here? Next, take on next one please. Resistance P, Q, R and S. Resistance P, Q, R and S resistance P, Q, R and S are connected across arm AB, BC, AD and CD in the form of a Wheatstone network. Such that P is 10 ohms, Q is 15 ohms, R is 25 ohms and S is 50 ohms. Find the resistance to be connected across S. Find the resistance to be connected across S so that the network is balanced. So that the network is balanced. So that the network is balanced. If the cell is connected, if the cell is connected across terminals A and C. If the cell is connected across terminals A and C. Fine. Now, let's see this. I can say that for balancing, if the network is balanced, then I can say that P upon Q should be equal to R upon S, right? R upon, instead of S, we will call this as Y. That will be my equivalent resistance of S and X. So P upon Q, P is what? 10 upon Q is R, 25 upon Y. Therefore Y will be 15 into 25 upon 10. 5 3s are, 5 2s are. So 75 upon 2, right? But what is Y? Y is nothing but S and X in parallel. I can say but Y is X and S in parallel. Therefore I can say that 1 upon Y is 1 upon X plus 1 upon S, right? 1 upon, you know the value of Y, you know the value of S, you should be able to get the value of X. The answer for this sum should be 150 ohms. Yes. Next. Okay, so do we get this thing clear? How you are supposed to balance a Wheatstone network? Okay, next let's move on to the next part, guys. Let's see a meter bridge. Right? The next thing that we will see is a meter bridge. Now, what is a meter bridge? A meter bridge is a simple experimental arrangement.
That's R4 is 12 and R4 is 4.
Huh?
First sum. R4 is 12 and R4 is also 4.
R4 is the equivalent of 12 and X in parallel. Right? Therefore, I've written R4 separately. These are two resistances in parallel.
Down there. You have written R4 is 4 ohms and but R4 is also 12 ohms.
R4, I've done the representation separately. We call this as say Y. So Y is equal to 4 ohms, but Y is 12 ohms and X in parallel. Right? Okay. Now, so you will get your value of Y here as 12 and X. Next, let's move on ahead, guys. Now, what is a meter bridge? A meter bridge, guys, is a simple experimental arrangement. A meter bridge is a simple experimental arrangement intended to measure an unknown resistance. Right? A meter bridge is a simple experimental arrangement intended to measure an unknown resistance. Fine. So that is what is a meter bridge. It is an experimental arrangement intended to measure an unknown resistance. Right? How does it work? It works on the principle of Wheatstone network. It works on the principle of Wheatstone network. Fine. Hence, it is sometimes also known as the Wheatstone network bridge. It is also known as the Wheatstone network bridge. Okay, let's see the experimental setup. It consists of 3 metallic plates right. It consists of 3 metallic plates A, B and C. A, B and C, in which you have 2 resistors connected. This is your resistance X, this is your resistance box R. Then a wire is connected across A and C, right, which is then connected to a power supply, a key and a rheostat. Right? A galvanometer is connected from strip C onto the wire. Right? So let's see the working of a meter bridge, or first let's see the construction of a meter bridge. A meter bridge consists of a a thin uniform conducting wire AC, a thin uniform conducting wire AC, thin uniform conducting wire AC, where 1 meter long, which is 1 meter long, and stretched on a wooden board It is stretched on a wooden board. In between, 2 thick copper strips are bent as shown in the figure. In between, 2 thick copper strips are bent as shown in the figure. Right? The third copper strip is placed on the wooden board such that it forms 2 gaps between the 2 strips. The third copper strip is placed on the wooden board. The third copper strip is placed on the wooden board such that it forms 2 gaps. With the 2 copper strips. Fine. Now, an unknown resistance X, which is to be determined, is connected in 1 gap. An unknown resistance X, which is to be determined, is connected in 1 gap. Right? And the resistance box is connected in the other gap. And the resistance box is connected in the other gap. So known resistance in one gap, unknown resistance in the other gap. A cell E, key and a variable resistance R are connected in series with the bridge wire. A cell E, a key, K and variable resistance R are connected in series with AC, with the wire AC, right? One terminal of the galvanometer is connected to a junction point B. One terminal of galvanometer is connected. One terminal of galvanometer is connected to junction point B. Junction point B. One terminal of the galvanometer is connected to junction point B of resistances X and R, and the other terminal is connected to a sliding key, and the other terminal is connected to a sliding key. Fine. To determine the unknown resistance, a suitable resistance is taken from the resistance box and current is sent through the circuit by plugging the key. To determine the unknown resistance, to determine the unknown resistance, a suitable resistance is taken from the resistance box. A suitable resistance is taken from the resistance box and current is sent through the circuit. And current is sent through the circuit. Current is sent through the circuit. Now, by touching the jockey on different points of wire AC, a point of contact D along the wire is determined by, you've done this experiment in lab, guys, I presume. By touching the jockey at different points of the wire, AC, a point of contact D, a point of contact D along the wire is determined. Along the wire is determined. A point of contact along the wire is determined such that the galvanometer shows zero deflection. Such that the galvanometer shows zero deflection. So I'm going to find out my null point, right? So therefore D will be the null point. Therefore D is null point. Once I know my null point, then I can say that distance Lx and Lr of the null point from ends A and C can be measured. Can you see this? This is my point D. This is going to be my distance Lx, and this is going to be my distance Lr. Right? Do we get this thing clear? Now I can say that distance Lx and Lr of the null point, distance Lx and Lr of the null point from ends A and C of the wire are measured. Right? Now I already know the value of x and r. I can say that x and r and the resistance of Lx and Lr of the wire form the Wheatstone network. I can say that x, r and resistances of lengths Lx and Lr of the wire form Wheatstone network. Fine. Now, in balanced condition, I can say x upon r is going to be nothing but resistance of length Lx upon resistance of length Lr right? That means now let's assume that rho, now let's consider that sigma is the resistance per unit length. If sigma is resistance per unit length, then in that case I can then say that x upon r is going to be sigma Lx upon sigma Lr, right? Sigma gets cancelled, so I'll get therefore x upon r is going to be nothing but Lx upon Lr. So that's going to be my equation to determine the unknown resistance using a meter bridge, right? Now, what are the sources of error in determination of unknown resistance in the meter bridge? Fourth, sources of error in determining unknown resistance are using meter bridge. Right, first, while deriving the formula, it is assumed that the meter bridge wire is uniform and the resistance per unit length of the wire is same throughout. But in practice, a bridge wire is not uniform and therefore errors can be introduced in the calculation of unknown resistance. We have assumed that you are going to have a wire of uniform, the wire is uniform and hence it has uniform resistance per unit length, but in practice it is not possible to get such a wire. So the first error that you can have is, I can say that while deriving the formula, it is assumed that bridge wire is uniform. It is assumed that the bridge wire is uniform and the resistance per unit length of the wire per unit length of wire is same throughout. is same throughout, right? But in practice, a bridge wire is not uniform. But in practice, a bridge wire is not uniform. A bridge wire is not uniform, and therefore error can be introduced. And therefore error can be introduced. Right, that's the first source of error. Second, you can have contact resistance that can be developed at the points where the wire is in contact with the copper strip. The wire is in contact with the copper strip, so at that point there will be some contact resistance, hence an error can be introduced. I can say second error is contact resistance. Contact resistance are developed. Resistances are developed. Contact resistances are developed at the points where the copper strip and wire are in contact, or where the wire is fixed to the copper strip, right? Hence an error can be introduced due to these contact resistances. Hence an error can be introduced due to these contact resistances. Fine. So these are your sources of error. These are your sources of error in a meter bridge experiment, right? Now let's try to find out. Let's use Kelvin's method to determine the resistance of the galvanometer. By using a meter bridge, I am able to get the value of, the unknown resistance. What if I want to find out the resistance of the galvanometer? How do I find out the resistance of the galvanometer? Now this is called as Kelvin's method. Right? Kelvin's method to determine the resistance of galvanometer. To determine resistance of galvanometer. Right? Same. First you have the meter bridge arrangement. The only thing is that instead of the unknown resistance, put a galvanometer in position of an unknown resistance. Right? And move the jockey till the galvanometer shows zero deflection. Right? Now let's see this. I'll just draw the diagram first. You need 3 copper strips. So your first strip, second, third strip. This is your meter bridge wire. Contact points A and B or A and C connected to a cell, key and variable resistance. Fine. Now you have galvanometer connected in one of the gaps. And you have a known resistance connected in the other gap. A known variable resistance. We're going to connect the jockey directly to the wire. Fine. Let's assume that this length is say LG and this length is LR. This resistance is R. Right? Now, in order to find out the resistance of the galvanometer, this is the experimental setup required. I can say that the galvanometer whose resistance is to be measured, galvanometer whose resistance is to be measured is connected. Galvanometer whose resistance is to be measured is connected in one gap of Wheatstone network. Is connected in one gap. Is connected in one gap of the Wheatstone network. Wheatstone network while known resistance is connected in the other gap. Known resistance is connected in the other gap. Fine. Now you have the cell, key and the rheostat which are connected in series with the bridge wire. Cell, key and rheostat, that's your variable resistance, are connected in series, with bridge wire. Are connected in series with the bridge wire. A jockey is connected to the junction of the galvanometer and resistance. A jockey is connected to the junction of the galvanometer, connected to the junction of the galvanometer and resistance box. Fine. Now, a suitable resistance is taken from the resistance box and the key is closed to send current through the circuit. A suitable resistance is taken from the resistance box and key is closed to send current through the circuit. Right? The rheostat is adjusted so as to get a suitable deflection. The rheostat is adjusted to get a suitable deflection. Right? The deflection of the galvanometer is noted without touching the jockey points to the bridge wire. The deflection of the galvanometer is noted without touching the jockey to any point on the bridge wire. Fine, do we get this in here? Now the jockey is touched at different points of the bridge wire. Now the jockey is touched at different points of the bridge wire the jockeys touched at different points of the bridge wire AC, and the point bridge wire AC and point D is found on the wire such that point D is formed on the wire such that the galvanometer again shows the same deflection. The galvanometer again shows the same deflection. The galvanometer wire again shows the same deflection with or without contact. With or without contact. Fine, do we get this in here? That means I can say that the length of the wire between point D and the two ends are noted. The length of the wire between point D and the two ends are noted. Fine. In which case I can say that the null point is not obtained in Kelvin methods. Kelvin methods is based on equal deflection method, right? It is certainly not the null point method. Now, I have already found out the length. So by using my Wheatstone, if G is the resistance of the galvanometer, I can say if G is the resistance of galvanometer, then under balanced condition, I can say G upon R is going to be Lg upon Lr, right? I can say that G upon R should be equal to Lg upon Lr, and that's how you will come to know the resistance of the galvanometer, when I can say that G is equal to R into Lg upon Lr. Fine, do we get this thing here? Now, what are the errors here? You have the same errors in Kelvin's method as you had in meter bridge. It suffers from the same errors that the meter bridge has. Right? It suffers from the same errors that the meter bridge has. That is, it will still have the same errors, that is, the wire will be not of uniform length, that is your meter bridge wire, and there will be resistance at the point of contact. Fine? Right. We'll stop this here for the day. Thank you very much.